Hello. So anybody can hear me? Hello, can you hear me?
Yes, I can hear you.
Okay, thank you. So today we also have three other slides needed to learn. Then we first learn network O&M and network troubleshooting. The last is network cutover. So compare with the queues. This is three slides. Just some useful skills when you do the network troubleshooting O&M. Okay, some basic knowledge, and I think it's easy to understand. So first, somebody have asked when we can get the training material. This for this slide, they are all same with the HCIP, advanced routing and switching. So this slide are the same with the HCIP, advanced routing and switching. So you want to see the material, you can just search for the HCIP, advanced routing and switching. Okay, so let's first learn the network O&M. Network O&M. Okay, so routine maintenance and troubleshooting are required to ensure the proper running of network function. Routine maintenance is prevented and planned maintenance, and troubleshooting is event-triggered maintenance. But this slide, we only focus on the routine maintenance. And the next slide, troubleshooting. We'll learn in next slide. So this course describes the precaution for routine maintenance and common tools, and some common tools such as the capture packet, and LLDP, So this is the main knowledge of the slide. Let's begin. First, we see the routine maintenance. Here we'll give some very useful command when you use. Okay, so the left side of a network involves network planning, design, network implementation, and network maintenance and optimization. And network maintenance involves routine maintenance and troubleshooting. So routine maintenance is performed to prevent the problems and minimize the possibility of unexpected faults. So fault codes found during the troubleshooting can be used as a reference for routine maintenance. So that's why we need to do network maintenance. Okay, so routine maintenance, we can obtain various parameters of the network that is working properly, such as the network device version, network bandwidth, and network security parameters. This will help you rectify faults. First, we see the classification of routine maintenance. Routine maintenance involves two types. First is device running environment. For our network engineer, we usually didn't pay more attention on the device running environment. Okay, for the running environment, we can see it contains the hardware running environment. We can see the for the equipment room and the power supply system and the heat dissipation system. So the hardware running environment is the basis of the proper running of device. Okay, to maintain the device running environment, an engineer has to visit a site in person or use some professional tools to observe and assess the environment. Okay, but this is usually by uh, uh, some assistant by network engineer of network engineer. There is device software and hardware running status. So this is what we focus on. This is what we focus on. The running status of software and hardware is closely related to specific service running our device. So network engineer must be familiar with the common maintenance command, such as display version, display configuration, and so on. This is provided by VRP. Maintenance personnel can maintain the software and the hardware of a device on site or remotely, mainly by running display command. So either of the following method can be used to perform routine maintenance. We can on-site observe the hardware running environment of device, or remote operation to check the running status of the software and the hardware of device. First, we give you a checklist for routine maintenance. This is a checklist. We can have 1, 2, 3, 4, 5, 5 different type, such as equipment environment check, basic device information check, and the device running status, interface content, and service check. Let's say them one by one. First, we checklist the equipment environment. We can say what we need to check: whether devices are placed reasonably, and the equipment room temperature. So the equipment room temperature, and the equipment room humidity, whether an air conditioner is working properly, cleanness. So whether the energy system is working properly, and so on. Then we can use this command. We can say some of them. For example, the cleanness. We use the method 2, observation. We can all items are clean and tidy without obvious dust. So clean or replace the dust filter in time to ensure proper vision and heat dissipation of cabinet doors and fan trees. So this is one as an example. So I think you can see the slide. After you receive the material, and for now you can just see the slide in HCIP, advanced routing and switching. Okay. Then we see the basic device information. So we also give you some example. Version of our running device, and the software package, information center, and the license information and configuration. So we also give you some command. So if you want to check the version of your device, you can run display version, this command, and the PCB version and the software version of the board meet the requirements. We can also see the system time. We use the display clock. So the system time must be consistent with the time used on our network management server. It means we must be the same with the IMS, because if the time is not the same, we will when we see the trap, it may be a little difficult to associate with zero time. Okay, this is for the system time. For the configuration, we can use the display current configuration. We can check whether the device configuration is correct by viewing the correctly effective configuration parameters. So we just see some of them. Okay. Third is we check the device running status. Device running status. How, for example, we can see here, boot running status, device reset, device temperature, and CPU status, memory usage. We also give you some command. We can see here. For boot running status, we use device. We can see this line. So we can display device, check where the in position status and the working status of our board are normal. So the online value is present, and the power value is power on, and the register value is registered, and the value of alarm is normal. We can also check the fan status. We use display fan, and the CPU status. We use display CPU usage. We use display CPU usage. So I think this command and the check item is easy. Okay. Then we also check the device interface. So for the device interface, we can check this item. Error package on interface. And interface negotiation mode. Interface configuration. For this two, we can use the display interface. So when services are running, check whether there are error packets on the interface, including CRC error packet. We can also see the number of incoming broadcast packet and the number of the unknown packet. Okay, we use the display interface. We use the command display interface brief. We can see the up-down status of our interface. The up-down status of the interface. Okay, that's some of the device interface check. Okay, we also can check the service running status. Here also some example. For OSPF, we can display OSPF pair. I think we may use this command very common. Okay, because we have learned the HCIA and the HCIP. Okay, the state value is 4 or 2-way. 2-way is just in NBMA network. Okay, you can also check the MSTP. We use this command, display STP brief. STP status value of the designated port and the root port are forwarding. So it must match the data plane, and the VRP. We use display VRP, and we see the device that is designed to be at a master state. Then we see the routine maintenance, software and configuration backup. So the purpose of backup is to restore network function in extreme case. So backup is to transfer files to a backup server. There are many backup methods. Generally, a device function as an FTP or TFTP client and transfer the server through the CLI command. Okay, you are advertised to backup configuration file every week. We can also backup the configuration. Okay, and the software and the configuration need to be backup. The purpose of backup in this scenario, we just see one of them. So service storage will be delayed without a backup configuration file. In the case of hardware, for the induced switch start failure or replacement by a device of the same module. So we must have the configuration backup. Okay, that's what about the routine maintenance. Routine maintenance. We have learned 5 types of routine maintenance. Then we learn the second part. So information collection tools. Here we'll introduce some very useful tools when you do troubleshooting. First is the information center, and this is provided by VIP itself. VIP itself. Okay, first we see the information center. I think when you configure the device, you may find some information is provided by the device itself. For example, if the interface is up, it will jump a line to running you. So this is the function of information center. Okay, the information center is an information hub on our device. We have 3 types. Okay, first is the log information, and trap information, and debugging information, information. Okay, we'll learn these 3 different information types, and we'll give you an example. Okay, we first see the log information. What is it contain? The first is user log. Record the user operation and the system running information. The user operation. For example, if you change the IP address of an interface, so in the user log, the user log will record it. Okay, and the security log record information about account management protocols, attack defense, and attack defense status. Then is the diagnostic log, record information in the help locate faults. So for trap information, we can see here, trap record system status information, for example, faults. So this type of information is different from log information. So the major characteristic of trap information is that administrators must be notified and alert immediately, and the trap information is sensitive to time. I say the trap information. So usually we configure the trap to use SNMP protocol, send it to the network management system. Okay. Debugging information. Information is output by a device used to monitor the internal running of the device. So the device can generate debugging information only after the debugging of a specific module is enabled. So we also give an example later. We must debug OSPF packet. For example, we'll see it later. So then we say the information severity. For whole device, the information is classified into 8 levels based on its severity and urgency. Lower value indicates a higher severity level. We can see 1 to 7. Okay. I think we just say 1 of 8. We see the severity of running. So a device running exception may cause a service fault. For example, a routine process is disabled. A packet loss event is detected by BFD. All incorrect protocol packets are deleted. So this is the description for warning severity, and this is all defined by the device. So I think you need to you need to change it. Okay. When you use it, you just find the production document. Okay, and debugging is informational only, and no action is required for the debugging. And this is most high level need to process immediately, emergency. You can see example, a program exception causes the device to restart or memory usage is incorrect. This is emergency. Okay. We have learned that the information center, the information classified into three types: log information, trouble information, and debugging information. So how can we get this information? We use information channel, and this is the terminal we view. We can see for the default channel we have 0 to 9. 0 to 9. We can see 1 is console channel, and 2 is monitor channel, and this 2 ID 2 log host, trap buffer, log buffer, and SMP agent. So here is where we can see the corresponding information. So I think if you use console interface to log in your device, you can see all the information, because we can see this line and this line and this line. They all point to the console channel. Okay, console channel. And then we say one of the trap information. So for trap information here, usually the device runs the SMP agent and this is NMS server. This is NMS server. So we can use the NMS to output the traffic information to see some warnings. And for debug information, we must run special command. Okay, because for different type of information, the information it provide may be very large, So we can do information filtering. So here the information filtering table provides the following information. So we can based on the sequence number of an information module and the status of the log output function, the level of log information to be output, trap output status. We can also configure on device, and we'll give the command in the slide later. Let's say the information output format. This is the log output format. I think you needn't to remember the format. You just need to understand the meaning of the information is enough. Okay. But here we just list the format. Okay, this is a log. For log, we can here it has special symbol. This is a trap. For log and the trap, they all have timestamp, and the host name So okay. We see some scenario of the information center. One is outputting log to a log host. We must configure the IP address of the log host. Then all the log information will send to the log host server. Outputting to an NMS, we use SNMP trap. Outputting debug information to the control. Must run the debug command. Okay, first, then we learn some basic command for information center. information center enable information center enable. So by default, the information center is enabled. So I think if you wanted to see the information, you can run the command undo information center enable. Undo information center enable. Okay. We can also specify the name of an information channel with a specified ID. We have run the ID is from 0 to 9, and the default name. We also have the default name. This is 0 to 5. This is all default name. So with the command, you can change the name for different channel number. We can also enable the log buffer function, information center log buffer. By default, a device is enabled. So sometimes you find that the information center we never use any command to configure, but the device itself has enabled the function. Okay, here is the terminal monitor. By default, the console is enabled to display information. A user terminal is disabled from displaying information, and the terminal debugging. That means we can see the debugging information. Terminal logging. A terminal is enabled to display logging information. So by default, the console, the console channel have all the information. But if you use Telnet, you use Telnet for VTY. I use VTY Telnet. I think you must run the corresponding command because by default, some value can't be seen in VTY mode. Okay, this is some display command, display log buffer, display log file. We can display the trap buffer and display debugging, and see the status of information center. Okay, this is example configure the information center. For the information center, we can see here we use through the console and check the following information: trap information, log information, and debugging information. We can also see here all these command is enabled on the device. Okay, we display channel. So we can see the channel name of the device and the severity of the severity level and the severity level. And this is the trap we see in the trap buffer. Here we can see this is the ID. So you can search the key key value in the corresponding product document. Okay, this is something about the LLDP. This is the log, display log CLI. We see the everything you input in the CLI. Here is the time. This is here we can see first we input the system view, then we configure the interface. And then is the IP address. And quit. That means we configure the IP address of R1. And when we configure OSPF, we can see here it may inform you the state of the OSPF state, two-way, NI, and the last 4. So the OSPF enable state change. One is automatically here is automatically displayed in the log format on the console port. The last is debugging. We can run the command debugging OSPF packet. So we can see here as an example. Here as an example. Okay, we can see the source IP address because the hello packet, the other hello packet is encapsulated in broadcast mode, and the destination address is 224.0.0.5. We can see the version type, and the packet length. This is the root ID, root ID. And the DR and the BDR, and where we use the authentication and the network mask, network mask. Okay, and the hello and the data interval, and the option E, and that means it supports type 5 and type 7, type 5 RSA. Okay, so with the debugging command, we can see why the OSPF neighbor is not normal. Is not normal. Okay, this is the debugging command. For Huawei device, we also provide packet information obtaining. We just use one command. So here, when the service traffic of a device becomes abnormal, for example, the traffic status is inconsistent with the traffic module, you can use the packet information obtaining function for analysis. We capture packet interface G000 destination terminal. It means the VTY interface. VTY interface. We can see here packet 1 and packet 2. Packet 1, packet 2. Because because it's not translate normally, I think you must calculate yourself. Okay, this is an example. RF for 48 bit. So this is destination MAC address. Destination MAC address R5, and this is the source IP address. Source IP address. And we can see here the 0806 in layer 2. Destination MAC, source MAC, and the type, type. Here is 0806. That means ARP. That means ARP. It here is 08, and that means the up layer is IP packet. Okay. Then we see LLDP. LLDP is the link layer discovery protocol. And is a link layer topology discovery protocol defined in IEEE. This ID. So we can use LLDP to find where the interface is connected correctly, based on the topology. So we can see first run the command LLDP enable. When the device enable LLDP, then we can use the command display LLDP enable. You can see G00 has one neighbor, R1 has one neighbor. We can see the system name, the name of peer device, and the system description. We can see it contains Huawei AR000 and the VRP software and the version, and the peer interface port ID, and peer management IP address, Okay, this is LLDP. Last is traffic statistic collection. Traffic statistic collection. We use MQC. Use MQC. So traffic statistic collection helps you to learn about traffic passing and discarding after a traffic policy is applied. So you can analyze and determine whether a traffic policy is properly applied or locate focus. For example, if R1 send a packet to R2, for example, if it is a SAMP packet, but for R1, it can't receive the reply message, SAMP reply. So maybe this switch, SW1 drops the packet, or maybe R2, this interface drops the packet. So we can, in this scenario, we can use the traffic statistic. We first create the ACL, and we find the source IP address of the packet. Source IP address of packet. This IP address, and then we configure traffic classifier. We match ACL, and we configure traffic behavior. In this behavior, we input this command, statistic enable. That means the traffic will be all numbered. And for create a traffic policy, we bound the classifier and the behavior together. And last, we apply the traffic policy on an interface. Here we run a traffic policy P1 inbound. This is the name of traffic policy, and the inbound. That means this direction. That means receive the packet from the direction of received packet, of receiving packet. Okay, here the preceding command output shows that R2 doesn't receive SAMP message. Okay, doesn't receive SAMP message. Based on the preceding information, you can check whether a fake link is fault. Or where the VLAN configuration of SW1 is incorrect. If this interface is VLAN 10 and this interface is VLAN and 20. So in this way, R2 can't get the SAMP request the packet. So that's why we use traffic statistic collection. Okay, let's see the quiz. Which of the following statements about the network maintenance function are correct? The routine maintenance is a type of preventive work. Routine maintenance helps you to obtain the network baseline, which lays a solid foundation for troubleshooting. The routine maintenance process high technology requirements for operation, but don't pose high requirements for operation standardization. So this is wrong. A, B, and D. Okay. Packet information obtained by R2 can be displayed only on the CRI of a device, cannot be saved in a file. This is false. R1 and R2 are directly connected. If the interface IP address of R1 and R2 are on different network, names of the two devices cannot be obtained using RDP. This is also false because RDP is just like LACP, or STP, it's run in layer 2. It's have nothing association with the IP address. Okay, let's see summary. In this slide, we learned the network maintenance, routine maintenance. We have given you some example and some very useful command. Okay, we also introduce some tools for obtaining information, such as the packet information obtain. obtaining, and traffic statistic collection, and LLDP. Okay, we have learn the tools for to gather the information in O&M. O&M. Then the next we learn the how to use the information we get to do network troubleshooting. To do network troubleshooting. Okay. Let's see an example for network troubleshooting. This course describes common network faults and how to troubleshoot them in an effort to help a network engineer build the capabilities of troubleshooting faults in various scenarios. It contains two parts. First is the theory, troubleshooting theory, and second is an example, troubleshooting example. Okay. If you have learned the slide in HCIP route and switching, so you may be very similar with the slide. So what is network fault? Network fault. Network fault refers to the phenomenon that our network lose a specific function and adversely affect the service due to some reason. So from the perspective of user, any phenomenon that adversely affects the service can be defined. It means anything affects the service, it can be defined as a fault. And here list some category and symptom for hardware. Hardware, if the device hardware have fault, it may cause packet loss. It may cause packet loss, and the device will also give you an alarm. Okay, so mapping between the preceding fault symptoms and the categories varies according to different scenario. This is just give you an example. Then we learn the troubleshooting process. It's just a suggest. So when you do troubleshooting yourself, I think you may use your own method. You may use your own method. Here, just to give you a suggestion. We can see for overview of the structured network troubleshooting process. It has these steps. Step first, report, first confirmation and information collection, identification and analysis. So we give the cause listing, and we do further assessment, and the last we step-by-step troubleshooting. We check whether the fault is rectified. At the last, we wrap up work. Do some wrap up work. Okay, this is we have list all the procedure for troubleshooting theory. First is the first report. For the report. So why we need this step? Why we need this step? We can see here. That's because generally the person who first process network faults is from a department related to service, rather than a network engineer. Okay, it means with the service first found the network fault. The network engineer often receive calls for help, such as the other people just tell you the computer can't access the internet, or the web page can't be displayed normally, and the game is stuck. So when you receive the report, I think here recommend you to record these things for the reporter: the name, department, position, work content, computer location, and fault frequency. Check where the fault occurs suddenly or frequently, and the user operation. Ask the operation before the network fault. Whether somebody changes the IP address or DNS parameters. Okay, so whether we open the desktop firewall, then we do further confirm, for the confirmation. Four factors for determining a fault: a subject, network service become the fault or faulty, symptom of the fault, and time and location. Describe the fault symptom accuracy. Then you can check whether the fault is within the responsibility scope. It is where related permission have been granted to rectify the fault. I mean, you must get the mission permission, get the permission when you do troubleshooting. Next is information collection. We run command on involved device. We can also use information collect tools, such as the information center. We introduced in the last slide. Okay. When we collect the information, then we do the identification and analysis. So by assuming the fault, maintenance and version specific change information and using team experience, you can obtain the list of possible cause for network fault. For the information, maintenance information, change information, time, then we got the cause listing, or possible cause 1, possible cause 2, possible cause 3, 4, and so on. And then we pass the impossible reason. We just leave some of them. Then we do the further assessment. To do step by step troubleshooting. Troubleshooting. Okay, in the phase of step by step troubleshooting, the conflict between the urgency of solving problem and the risk of introducing new fault must be balanced. So user must be clearly informed of the risk that may be include the process, and perform the check only after being authorized. Must do emergency plan, rollback reparation, step by step troubleshooting. Then we check where the fault is resolved. Okay, so after the root cause is found and the fault is rectified, the troubleshooting is complete. After the fault complete, we may do the conditional observation, and last do some wrap-up work. Wrap-up work involves arranging related documentation and sending notification. We back up all changed configuration of software in the private network troubleshooting process. So here is some advice for document handover, troubleshooting process documents, and troubleshooting summary report, and change backup, maintenance, and suggestion. So if you have passed the HCIE, routing and switching, Oh, I'm sorry. For if you pass the HCIE Chinese version, you must write a tag. Write a tag. It just is the tag is a wrap up work. This means you must write down how does you deal process the network fault, the procedure you do. Then we learn the core idea and the method, some basic method for network troubleshooting. The core method is service traffic path-centric troubleshooting ideas. We find the traffic path, for the network layer. Multi-paths may exist during packet forwarding. So therefore, you need to determine the path over which service traffic is transmitted based on the packet forwarding process. You must find the right way to the destination address. For the data link layer, we can check how data frame. We check the data frame of service. We use display STP. And see the port rule. DP, DPRP, AP, and the status of the interface. Here list is a layered troubleshooting approach. We can process the fault from up to from the lower layer and to up layer. For the physical layer, you can see here. For example, we can check where the physical status of an interface is up and where cable and connectors are securely connected. Then we can see here. We also have some other method, configuration comparison approach. Compare configuration, software version and hardware module in normal and faulty. We see the normal device and the faulty device. We compare them. Here is the configuration that we have last version, and this is the new version. We can compare them. We can find somebody have changed the ED timer hello interval. So we must change it to the timer 30 based on your own network. Here is a block-based troubleshooting approach. If fault occurs, you can narrow down the fault locating scope by classifying the fault into one or several categories. Management for root name, password, service, and log. For ports, the IP address, and cap solution, cost, and authentication. Where is the routing protocol fault occurs. For static root, RIP, OTPL, BGP, and route import, and so on. Here is an example. We use display IP routing table. We find only directed route are displayed. We can see the fault is related to the following blocks: routing protocol, policies, and port. So if no routing protocol is configured, or routing protocol is incorrectly configured, so the routing table may be empty. Or you may also configure ACL is incorrectly configured, so make the device only have direct route. Then we can see here is a segment-based troubleshooting. For the packet to the internet, we divide the path into 4 segments. Segment 1, 2, 3, 4, and we check check the cars one by one. Replacement approach. Replacement. The replacement approach is one of the most common method. One of the most common method for checking hardware. Using in this scenario for hardware problem. Hardware. So if our network cable may be faulty, we can replace the network cable. Replace the network cable with a good condition. So if an interface module may fail, replace it with another interface module that is working properly. We can also replace the device, replace the PC, replace the switch. Replace approach. We see summary for network troubleshooting. Requirements for network maintenance and management personnel. To have an in-depth understanding of protocol requirements. So I think this is the most important. This is the most important. So be able to get a customer to describe the fault symptom and related information in detail. Fully understand the network managed and maintained. So you can use multiple troubleshooting approaches. Okay. It need you have a lot of skill for troubleshooting. Okay. The second part shows an example for troubleshooting. We classified the fault into 3 types: layer 2 faults, and root faults, and service faults. Here, service faults, we use DHCP as a service. For root fault, we say the static root. OSPF, easy, and the BGP. For the LAN fault, we give you the VRP, and STP, VLAN. It contains this technology. Okay. First, we see the troubleshooting topology. Okay. Yeah, we have PC1, PC2, PC 13, 14, PC5, and server 6. Server have some application, and we can see the routing protocol. Here list the routing protocol for R1 and R2. R1 and R2. We run OSPF. And between R2 and R3, the IGP we use easy. And BGP is run between R1 and R2, and R2 and R3. So R2 act as RR. R2 is router reflector. So we also use static root for PC to communicate with each other. They must send the packet to the gateway. Gateway is on SW5, SW4, SW3. This is the gateway. And for the switch, we configure static root to R1. Here we configure static root to send the packet to R3. We also configure static root to this direction. Next hop set SW3 or SW4. So here we introduce the routing protocol. We can just see this figure. I think This figure have show you all information. OSPF is easy. So for later, I think may cause this question because R1 and R3 use different IGP protocol. If R1 and R3 R1 and R3 wanted to communicate with each other, and we must do router import on R2. Okay, router import on R2, and for OSPF, the protocol must run correctly, and here the easy protocol must also run correctly. Okay, and this topology shows the IP address plan. Loopback 0 can see as 101.1 here because the device number is 1, so we use 100.1.1. So R2 is 2.2. R3 is 3.3. Okay, you can see the interconnection interface. So the network segment here we can 1013 1014. We can see this is just this device number and this device number, and the small device number is in left 13. So this is 1414, and R3 and SW5. So this VLAN 35, and this network is 35. For here, the network segment is PC1, PC2. So this is 12.0, this network segment, and it's PC13 and PC14 use 434, this network segment, and this 56, this network segment. Okay, we can see the IP address configured for the terminals. For PC5. PC5 obtain IP address using DHCP. That means PC5. PC5 using DHCP. Using DHCP to get the IP address. And R3 function as a DHCP server. Here R3 is DHCP server. DHCP server. So I think SW5 here must DHCP relay. DHCP relay. Relay. And SW1, SW2, SW6. This is all layer 2. Access layer. Layer 2 switch. So on SW5, we must configure DHCP relay. DHCP relay. Okay. Then we say the root advertisement planning. Advertisement on R2. Configure OSPF and EDEs to import the root from each other so that loopback 0 on R1 and R3 are reachable. OSPF EDEs, we make all the loopback interface can communicate each other. And R1 import root static destined for 12.0 this segment, and 3.4.0 this segment into BGP. That means this static root and this static root into BGP. Okay, because we want to PC1 and PC5 and PC6 and server 6 can communicate each other. So the root, the static root must send to the two peer, and also R3 must also import the static root to BGP. Only in this way, R1 and R3 may both have peer network segment root. Okay, R3 import the static root destined for this segment. Okay. For the layer 2 network, we run MSTP. MSTP. This is the MSTP planning. We can say the instance. We created two instances. instance 12 VLAN here, PC1 and the PC3. Oh, sorry, I must change it. PC1 and PC2 use VLAN 12, PC13 and PC and 14 we use VLAN 34, VLAN 34. Okay, we can see the root bridge. Now for the instance SW3 as the root. For this instance, SW4 as the root bridge, and the other is the backup bridge. So we must run root STP root primary or STP root secondary on different MSTP instance. Here is the VRP planning. For SW3, the virtual IP is this 254 for this segment, also 254 for the virtual IP address. And for the other device, the telnet name is Huawei, and the password is Huawei years 123, Huawei 123. Okay, we have three fault. First is PC1 and PC13 can't communicate. PC1 and PC13 can't communicate. And the second problem is server 6 provide FTP, but PC1 can't use this service. That means PC1 can't communicate with server 6. Okay. Third is PC5 can't communicate with any host. Okay, PC can't communicate with any host. Okay, for the PC1 and the PC3, because they just communicate in the same layer 2 network, we just configure this four device. For server 6 and the PC1, we must configure all the root, all this topology. PC5 can't communicate with any host. I suppose PC5 has not obtained the IP address because the IP address is configured by DHCP. So there is something wrong with DHCP configuration on R3 and the DHCP relay SW5. Okay, so we just give 3 network fault, for example. So assume that the symptom have been confirmed. We skip the following steps, such as we have introduced the fault report, fault confirmation, information collection, and the wrap-up work. We just configure the process to troubleshoot the fault. Okay, let's see the first fault. PC1 and PC3 can't communicate. We simplified the topology. Here. PC1, PC3. Okay. PC1, PC3. We just list the operation. We list the reason. Here is a physical link fault. Maybe we have a physical link fault. So this is a traffic path. Incorrectly configured IP address, VLAN configuration error, because it's a layer 2, maybe it have a loop, maybe it have a VIP fault. We'll focus on this item. Okay, let's see here. First is we check where is the physical link fault. Physical link fault. On PC1 and PC13, we choose control panel, network, and the internet and the network connection Ethernet cable. This is on our PC because PC1 is PC. We just find in this path. We check where the physical interface status on each involved switch. For example, we use SW1. We use display interface brief. Brief include up. We just say where the physical interface is up. Okay. Okay. Let's say all the interface is up. Then we do pin this IP address. Pin this IP address from PC1 and check where the number of packets is sent and received by the interface increase. If so, the physical link is working properly. So if not, we must replace the network cable. Okay, here is the result with display interface G0010. You can see the PVID is 12, TPID, TPID. And we can see input, input. This means the physical link is good. The physical link is good. So then we check PC's physical IP address is set to, and the gateway address is set to this IP address, correctly IP address, So we check IP address on SW3 and SW4 and ensure that the IP address are correctly configured. We use SW3 as SW4. We use VLAN AV interface. VLAN AV interface. 12.3, 34.3, 12.4, and 34.4. So we can see the IP address have been correctly configured. So since the IP address is right, then we check the VLAN configuration error. VLAN configuration. Let's say display VLAN. You can see VLAN 12 and VLAN 34. We can see tag G0010 and 34 tag G0010. This interface. Because this interface is directly connected to PC1. So by default, I think this interface must be set up to access mode. So here I think it's wrong. It's wrong because it's tagged. Okay, it's tagged. It's tagged. I think AOV config this interface access VLAN 10. It may be untagged here. So according to the preceding information, VLAN configuration of G0010 and G0011 on SW1 are incorrect. So we must change the configuration to right. This to port link type access and port default VLAN 12 and this interface link access and port default VLAN 34. Okay. After we correct the VLAN configuration, we then check where the fault is already rectified. Okay, we run the pin this command on PC1. So when we find a new phenomenon, the command output shows the packet loss occurs and the delay is long. So why what will cause this problem? Then we say check the MSTP status on each switch. MSTP status. So we display STP brief, then we see the MST ID, MST ID. We find SW4. All the interface is forwarding state, This means SW4 is the root bridge for all instance, but for the data plane here, for instance, 12, we want the SW3 as the root bridge. So the MSTP state doesn't match the data plane. So MSTP faults may be caused by incorrect domain name setting, incorrect the bounding between instance and the VLAN, and the incorrect bounding between ports and the VLAN. So we check MSTP configuration on SW4. And then we see the region name. Region name is test. But the zero name is in this manner. So we must change. We must input this command, rename test. Okay. After when we correct the MSTP configuration, we still check the domain name and the P. We still find the problem. As a result, packet loss occurs now and then. Okay. Then we may think maybe the MAC address flapping occurs. We use display MAC address flapping, this command, display MAC address flapping. Okay, you can see display flapping MAC record doesn't exist. After observing for a while, find that the fault occurs during working hours, only working hours. When the fault occurs, check the MAC address table and find that the MAC address table is unstable. During working time, a switch port frequently alternate between up and down. So we'll send a large number of TCP video. Okay, send a large number of TCP video. So in this case, configure the switch port connected to the PC as an edge port, because edge port will not send TCP video. Okay. After the fault is already rectified, we verify the reliability. So we shut down. G004 on SW3. Shut down this interface. In this time, PC1 can't pin PC13, causing a large number of packets to discard in a short period. So after SW3 is restarted, the following alarm is generated on SW3. You can see SW3 detect a duplicate IP address from the interface, and the MAC address is this ID. It means the VRRP ID is ID1. ID value is 1. So this IP address is a virtual IP address. Okay. So VRRP may be defective. So we obtain packet information on SW1. The address marked right. The address marked bold here. Not the bold here. We capture the VRID. This MAC address. The ID is 3. The ID is 3. The ID is 3. That means the ID of VRP is different. On device. On SW3 is ID1. On SW4 is ID is ID3. So we must change the configuration of VRP. So as shown in the preceding slide, packets are dropped between SW1 and SW2. So the destination MAC address is 00. So and the VRP ID is 3, which should have been 1 as planned. So we configure on SW3 VRP VRID. Three, change 3 to 1. Change 3 to 1. So after we configure this command, we found that no packet loss occurs during the switchover. Then the fault is rectified. For the line layer 2 fault, we check this term. Then we see next the root fault. Root faults. Now here we see the second problem. PC1 can't use the FTP service. We also simplify the topology. PC1 to server 6. So we also list the reason physical link fault. We assume that the physical link is good, and the server fault, and the server is also good. So we just check this root fault. A static root OSPF BGP it is all traffic control fault. So here when we say the data packets are forwarded hop by hop, our routing device along a path must have routes to the destination. So first check whether route destination for server 6 exists on all devices. So which data path sent from PC1 to server 6. That means this path. Okay. Check the static route configuration on SW3. Display IP routing table protocol static. You can see the command output should indicate that the static route has been correctly configured on SW3. That means if PC1 sent packet to SW3, SW3 set the routing table, then send to R1. R1 will also search the routing table and then forward to R2. R2 search the routing table, and R3 search the routing table, and SW5 search the routing table, and then send to server 6, to server 6. So we deal with the fault by segment, by different segment. 1, 2, 3, 4, 5, 6. Okay. Then we check the routing table on R1. Display IP routing table on this destination. So the command output shows R1 doesn't have a route. So we check where a BGP peer relationship is properly established between R1 and R2. Because this network is imported by R3 to import to BGP. Okay, import to BGP, and R2 is RR. So R3 send the route to R2, and R2 send the route to R1 use BGP. That's why we check. BGP R1. We can see here the state is idle. So then we must check why R1 and R2 can't establish BGP neighbor relationship. We can see this reason the loopback real interface of the remote device is unreachable, and the AS number of the local or remote device is incorrect. When eBGP, the peer eBGP max hop command must be used. The root ID on both ends are the same. Okay, so it may have this different reason. We just select one of the most possible. Okay, according to the command output, the number of sent and received packet are zero, indicating that the loopback 0 interface on the remote device may be unreachable. So on R1, then we check the root destination for the BGP peer, BGP peer 10.0.2.2. Okay, the command output shows that R1 doesn't have a root, because the loopback 0 interface is learned by OSPF. Okay, learned by OSPF. So we must check where the OSPF run correctly. We use this command, display OSPF peer. Display OSPF peer. OSPF process one, we find it has no OSPF neighbor. So why the OSPF neighbor relationship is not established, we can see here. May have different reason. Root ID on both ends are the same. Area ID don't match, and MTU don't match on both ends. On an MA network, the priority of all devices are set to 0. So in order to find the zero reason, we check OSPF error information on R1. Display OSPF error, and we only see the root ID. The number is not 0. It's not there. Root ID confusing. This means the root ID on R1 and R2 may be they are same. So the preceding command output shows root ID conflict may cause a failure to establish an OSPF neighbor relationship. To accurately locate the fault, we enable OSPF debugging. That's where we learn. Debugging in the last slide. Network O&M. Okay, we run terminal debugging and debug OSPF packet interface G000. This interface and debugging, and at the same time we check the configuration. Check the configuration on R1. You can see here display OSPF interface. Root ID. Local root ID is 10.0.1.1, and the IP address here is 10.12.1.1 here, and we can also see the DR and the tab, OSPF network tab, MTU, and the timer, hello timer and data timer. And then we check the debugging information. We can see here source address. That means here, source address 100.12.2, and the interface of here is .1. Okay, so the IP address is correct. Then we can see the tab hello packet, and the root ID here. We have both the bold font. 10.0.1.1. It's the same with root ID on R1. Okay, the same R1, and the hello interval and the data interval and the option, they are all same on R1. So after comparison, it is found that the interval at which hello timer are sent mask authentication information on the one and the match. On the other hand, only the root ID conflict occurs. So we must log in to R2. Okay, log in to R2 and change the root ID. Change the root ID on R2. But at the same time, we have another problem. R2 can't be telnet. Can't telnet. Okay. Common use cause of telnet login failure. We can see as follows. Root is unavailable. Telnet is disabled on the server. Or you configure ACL. Or in the VTY where you configure protocol inbound. SSH command uses because we use telnet. So the type must be telnet. Okay. So when we can't remote log in, we must log in use the console. Console port. We find that the telnet server is enabled, but in the VTY view, we found that the protocol only support SSH. So we must change the command protocol inbound telnet. Then we can telnet the device successfully. Okay. Then we configure the root ID on R2. Configure root ID on R2 and restart OSPF process to make the root ID take effect. We must restart the OSPF process. Okay, we can see the root ID address. We can see neighbor is up. Then we check display IP routing table for designated loopback 0 interface of R2. Here, cost is 1, and from OSPF. Then we check BGP peer relationship on R1. BGP, the BGP is already established. Okay. Then we check the routing table. We found that R1 still have no 10 this network segment. Still can't find this network segment in the network routing table here, because this route is sent or maybe generated by R3. So we must check R3. Display BGP routing table. We find R3 have correctly input route to BGP, but R1 hadn't learned it. Then we must check whether R2, because R2 is route reflect. R2 is learn the route. You can see here. We check the BGP peer status on R3. We find that the state is either. Okay, either. Then we see the display IP routing table for 102.2. This loopback interface of R2. We found the interface, the routing table can't find this route. So because R3 and R2 use IGP is easy. So we check the easy peer. We found that the neighbor relationship is good. But we can't find the can't calculate the route. Here we list the reason. Easy is not enabled on loopback 0. Maybe in this way. Cost style don't match. Routing policy is configured on the device. Network type doesn't match on both ends, and so on. So we display easy interface. We found the interface has already enabled easy, and then we check the configuration. We find the cost style wide is on R2. So we must also configure cost style wide on R3. On R3, we find that we lost this command. That means the cost style type is different. On R2, R3, and this result in R2 and R3 can't reach peer loopback 0 interface address. Okay, then we correct the configuration on R3. We display IP routing table. Here. We can see from it is. Then we check display BGP peer here. Okay, it's established. We can also find here R3 have already have the route designated for PC1. Okay, R3 also have, because it's network segment and it's internal and best and select. Okay. SPC R3 also already have the route designated for PC1. Then we check where R1 has a route to this way, to this direction. We can see the symbol is IGP, but it's not selected. It's not a best. Why? Which may cause this phenomenon. We check R1 has received the BGP route from R3, but the route is unavailable. So the possible cause is that the next hop is unreachable. Okay, the next hop, because next hop is 10.0.0.3. This OSPF, this is EE. Maybe because they are different IGP protocols. So R1 can't find a useful next hop. We display IP routing table. We find that. Okay, it's really can't communicate to 10.0.3.3. We list the reason here. Our routing policy is configured on R1. R2 don't import is the route to OSPF. Type 5 RSA are filtered out in the outbound direction of R2 interface. We filter type 5 RSA. Maybe this reason, okay? Then we deal with it. We display OSPF RSDB. We find on R1, we can't file type 5 RSA, can't file type 5, and we display R2. Okay, here, the R2 lost import is. Okay, so we modify the configuration of R2 and import is route into OSPF routing table, and then check the routing table of R1. You can see here, R1 has learned the IP address of R3. Then we trace route, because the route has already destined to PC5. We trace route. We can find that. And the last, we can't communicate again. Then we use the traffic statistic. Create ACL, create a classifier, create a behavior, and create a traffic policy, and use traffic policy on interface. We find right. Dropped is 0, and passed. That means R3 has sent the packet to SW5. We check the routing table of SW5 in the direction where server 6 sent the packet. We found that. SW5 doesn't have a static route to PC1. W5 lose the route to PC1. Okay, so we must configure static route as SW5, and after we configure, we find the troubleshooting is complete. PC1 and PC5 can communicate correctly. Okay, then we have this has processed the fault successfully. We have deal with this fault. We can see summary: incorrect static route. Incorrect static route. Failure to establish OSPF neighbor. Incorrect is route. BGP peer and BGP route. Telnet login and packet opt-in tool and the traffic statistic collecting tool and the tracer. This is our following tool. Okay. At the last, we learned the service fault. Here we can say PC5 can't communicate with any host. PC5 can't communicate with any host. The possible cause is that the physical link to PC5 is abnormal, or PC5's IP address is incorrect. Check the IP address of PC5. PC5 failed to obtain an IP address. You can see IP address is 00. So why PC5 can't get IP address? List the reason. The link between the client and the server become faulty, and DHCP function is disabled on our device. Maybe DHCP address. No IP address is available in address pool. So We check whether physical link to PC file is normal. Then we check where a layer 2 loop occurs on SW6. W6. Okay, nothing wrong. Nothing wrong. Here the VLAN ID. We change the VLAN ID. Okay, skip here. SW file is a relay agent. Query the global configuration. We find here DHCP select the relay server. Server here. Server is here. But the DHCP server has been enabled on SW5 and the DHCP relay agent has been configured. However, after the data packet sent by PC file passed through SW6 at the tag VLAN ID 56 to the packet before forwarding them. So we must configure this command on VLAN 56 because VLAN here is 56. We must do the command in VLAN 56. Okay. After the command here, PC file will still can't obtain. Then we check query a DHCP relay status of SW5 display DHCP relay static. You can see the DHCP packet received from client 11 discover 11 and send to server 11. It means this direction the packet is not loose. Then we check R3. DHCP select global on this physical interface. But we use the IP address is in server interface. Because this is VLAN 35. So on F3 the interface is server interface G002.35. .35. Display DHCP statistics. Okay, check IP address on PC file. So in this way, we have to deal with the DHCP server and the DHCP relay agent, and then PC file has obtained an IP address and can use it to communicate. All hosts. The troubleshooting is complete. Okay, that's what we learned. 3 different example for troubleshooting. Okay, this is the summary. The structured troubleshooting process, and this is something theory, and we also give you an example. Okay, so that's what I learned about network troubleshooting. Okay, do we have any question? Okay, I will have no question. Then Chris will introduce the next slide.
Now let's continue to have another lesson. This lesson is not a technical lesson. You will find that it introduces the